Welcome to Xiaolu.x, Learning in Motion. Today, we uncover the hidden power of latent collaboration in multi-agent systems. From subtle connections to adaptive cooperation, discover how agents find common ground and work together, often without being told to.
What actually slows down today's multi-agent AI?
Each agent plans in its own bubble. They don't see what the others are doing until it's too late.
So we open a shared memory and let everyone talk.
But that creates a new problem: constant chatter. Signals pile up, bandwidth is wasted, and decisions stall.
For years, agents wasted compute converting raw thoughts into clumsy strings of text. Every loop, every token, stolen cycles. The LatentMAS pipeline looked like this: fragment, serialize, tokenize, parse, and only then reason. Thought-native reason.
When updates travel by long text, heavy threads, information splinters, each forward, each reply is a chance for context to be lost and errors to multiply. Contrast that with a shared, structured update. Everyone sees the same source in real time, and one change.
What if models could share what they know, dense vector thoughts, without ever retraining? Traditional methods hit a compute wall. LatentMAS breaks it. A lightweight layer slides between models, translating representations directly, so knowledge flows instantly. One layer, many minds.
Imagine two language agents that can share their thoughts instantly. The secret is something called a KV cache transfer. Keys and values representing rich context are streamed directly from Agent A's memory into Agent B's without any recomputation. That's the KV cache.
From token usage in the old baseline versus the new approach. The drop is dramatic, down from 67 billion to just 4.3. That is a 93% reduction. Fewer tokens mean less overhead, faster responses, and big energy savings. Running the same workload, the new model draws only 89 watts while the old one pulls more than 400.
Line meet pipeline v5. On graduate level benchmarks, it finishes 7 times faster than the current baseline, without sacrificing accuracy. From fluid dynamics to graph matching, the new architecture unlocks higher resolution results in the same wall clock time. Optimized memory flow, new kernels.
Here's how the new LatentMAS model stacks up. On this radar chart, the blue shape is LatentMAS. The orange and gray areas are two widely used baselines. Accuracy jumps to almost 95%. Over 8 points higher than the Bayes baseline, and more than 13.
When we ask a model to think step by step, we often get better answers. But there's a catch. After a few steps, errors start to build up. Extra reasoning can actually introduce noise and knock accuracy down. The challenge is finding the balance, enough deliberation for clarity, but not so much that it drowns in its own.
In every field, breakthroughs are rewriting what's possible. From compact chipsets that power our AI, to solid-state batteries fueling clean flight, gene editing curing disease, and sustainable energy lighting the world. We are learning faster, reaching farther.
Welcome back to the Deep Dive. So, we spend a lot of time talking about what AI can do, but it's pretty rare that we actually look under the hood at how AI thinks.
Or even how AI systems talk to each other.
Exactly. And today, we're diving deep into a really fascinating research paper on that very topic. It's called Latent Collaboration in Multi-Agent Systems.
And it's a serious piece of work. It comes from a collaboration between Princeton, Stanford, and the University of Illinois Urbana-Champaign.
Our mission here is to figure out if we're finally seeing the beginning of the end for one of the biggest bottlenecks in advanced AI.
Mm-hmm.
So, okay, let's just unpack this. Have you ever wondered why, when you get multiple AI agents to work together on a really complex problem, like a big coding project or a math proof, why is it so often incredibly slow?
And expensive. Don't forget expensive.
And so expensive to run.
That is the exact core problem. I mean, we're deep in the era of agentic AI now. The expectation is that you can have these systems that, break down a task, coordinate.
Like a planner, a critic, a solver.
Right, all working together. But that very coordination is what's dragging them all down. It's the limiting factor on how effective they can really be.
Okay, so that inefficiency, that's what you're calling the old way.
Right.
How were these AI agents actually communicating before this paper came along?
Well, the traditional method is what the researchers call text-based multi-agent systems, or text-MES for short.
It's MES, got it.
And it's as simple as it sounds. Natural language, just plain text, is the common medium. It's the lingua franca. So if Agent A needs to tell Agent B something...
Or even just think to itself.
Exactly. Even for its own internal reasoning, it has to convert its deep, complex internal state into a stream of, discrete tokens, actual words.
It's like forcing two people who can read minds to collaborate by writing incredibly detailed reports back and forth for every single step.
That's a perfect analogy, and it is so incredibly wasteful. The whole process of generating and then processing these huge volumes of text tokens, it just consumes gargantuan amounts of computation.
So you get high token usage, which costs a ton of money, and you get really slow inference times.
Yes, but here's the really crucial part. The cost isn't just in resources, it's in the actual quality of the reasoning.
You're talking about error propagation.
Yeah.
Right. If I have to summarize my complex thoughts into a simple paragraph, I might miss some nuance.
Or worse, you introduce a tiny mistake, and the next agent in the chain just picks up that mistake and runs with it, amplifying it along the way.
Right.
The paper points this out directly. They say LatentMAS relies on lengthy textual exchanges that amplify early reasoning errors. They even give a specific case study from the GSM-8K math benchmark.
So what happened there? Walk us through that failure.
So a planner agent makes a small mistake early on in its text-based plan. The creative agent comes along, reviews the text, but the language is just, as they put it, unnecessarily convoluted.
So the error slips through.
It propagates, and in this specific problem, it was a problem about bees, the final solver agent gets this flawed, brittle, textual instruction and just fails the question. It gives the wrong answer, 15. The language itself was the bottleneck. It was a noisy, lossy channel.
Okay, so if the agents can't use slow, lossy language, what's the fix? This takes us to the new way, what they call LatentMAS. And this is where it gets really, really interesting. How do they talk without any words?
The breakthrough is moving the entire collaboration inside the models. It's continuous latent space.
Okay, so what is the latent space? Think of it like.
Think of it as the deepest part of the model's brain. It's where information is stored as these dense, continuous mathematical vectors, not discrete words like cat or dog. LatentMAS lets the agent share information right there, completely bypassing text.
And they did this with a training-free framework, which, I mean, that's remarkable in an industry that's all about constant, expensive retraining.
It's the defining feature. They're optimizing how the information is used, not retraining the model itself. And they do this with two core mechanisms.
All right, lay it on us. What's the first one?
The first is latent thoughts generation.
Okay.
So instead of making the agent output actual text tokens, its reasoning just unfolds by auto-regressively appending its last layer hidden representations.
Whoa. Okay, break that down. Last layer hidden representations.
In simpler terms, right before the model decides what word to spit out, it has this dense vector that contains everything it's calculated so far. That vector is the thought.
So the thought isn't the word 7, it's the complex, multi-dimensional vector that would have become the word 7 if you forced it to speak.
Precisely. That's the continuous state. By just appending those vectors one after another, the model is basically having a very sophisticated internal monologue, and it carries way more information than any single word ever could.
That makes so much sense. So that solves the cost problem for one agent thinking by itself. But how do you share that dense thought with the next agent? It sounds like trying to pass a dream from one brain to another.
And that's the second mechanism, latent communication via working memory. The key here is that they exchange this information using a shared working memory. And that memory is stored in the model's layer-wise key value caches, the KV caches.
Right, the KV cache. For anyone who needs a refresher, that's basically the model's short-term attention memory, right?
Yeah.
The thing that lets it remember context without rereading the whole prompt every single time.
Exactly right. It's what makes transformers efficient. So what LatentMAS does is it realizes, hey, we can just transfer this complete memory state, which has the original context plus all the new latent thoughts, directly to the next agent.
That is genuinely brilliant. You're not forcing the first agent to write a summary. You're just handing the next agent the complete, raw, unedited notebook of the first agent's entire thinking session.
Losslessly preserved. That's the key phrase. Lossless. You get all the raw, dense data without the compression or error that you get with text.
But wait a second. If you're just shoving these dense internal thought vectors back into the model, wouldn't that destabilize everything? I'd assume those vectors don't statistically look like the normal input vectors the model is used to seeing.
You've just hit on the crucial technical detail. The paper calls it the alignment trick. And you're right, the output embeddings do naturally drift away from the input embedding space.
So it would break.
It would break. To fix it, they use a simple linear alignment operator. You can think of it as a small, computationally cheap statistical translator. It just nudges the latent thought vector so it realigns with the structure the next layer is expecting. It's a tiny step, but it's what makes the whole thing stable.
Okay, so you've got cheap, fast, continuous vector transfer using memory caches and a little alignment trick. The theory sounds solid. So now we get to the demo. What do the actual results look like?
They're pretty unprecedented. They tested this across 9 different domains: math, science, code generation, you name it. And the efficiency gains alone are just, well, they're staggering.
Okay, let's start with the hard numbers. Token usage. How much did they save by going silent?
It's one of the most visually impressive demos in the paper. You look at the bar chart, and the text-MAS bars are these huge towers, and the LatentMAS bars are tiny little slivers. On average, they saw an 83.7% reduction in output token usage.
83%. Wait, say that again?
No, an 83.7%.
That's practically removing the entire processing cost. You're just getting rid of 4/5 of the work.
It confirms that human language is just way too clunky for machines to collaborate with each other. And that efficiency translates directly to speed.
What kind of speed up are we talking about?
On average, it was 4.3 times faster end-to-end. But on the really hard problems, like the GPQA Diamond benchmark, which is graduate-level stuff,
Right.
they saw speedups of up to 7 times faster than even a highly optimized text-MAS system.
7 times faster on the hardest problems. That completely changes what's possible. Problems that used to take minutes could now happen in real time.
Exactly. It lowers the barrier to entry for complex system-level reasoning.
But, okay, speed is one thing. What about accuracy? If you're thinking that much faster, are you making more mistakes?
That's the amazing part. The accuracy actually went up. It consistently improved performance. They got accuracy gains of about 2.8% to 4.6% over text-MAS.
And this is what we see in that radar chart.
Yeah.
Right? It's another great visual. You see the performance profiles, and the blue shape for LatentMAS it completely surrounds the others. It dominates.
It dominates. It shows it's not a trade-off. It's just better across the board. And to bring it full circle, it fixes those qualitative failures. Remember that GSM-8K-B problem?
Yeah, where text-MAS got the answer 15.
Right. The LatentMAS system, using that high-fidelity latent memory, it navigates the logic perfectly. It gets the correct answer, 75.
So it's not just faster, it's more robust.
Significantly more robust against compounding errors.
It honestly sounds like a pure upgrade. Better reasoning, huge efficiency gains, and no retraining costs. But there's always a catch. So let's talk about the catch. It's not a silver bullet yet, is it?
No, and this raises a really important question. The system is training free, but it's not tuning free. You still have to figure out, how much internal thought is actually useful.
What do they find? Is there an optimal budget for thinking?
There seems to be. They found that performance generally improves as you add more latent steps, but it peaks somewhere around 40 to 80 steps.
And what happens if you go beyond that?
If you push it to, say, 100 or 120 steps, the performance actually starts to decline slightly.
Huh. Why would thinking more lead to worse results? That seems a bit counterintuitive.
The thinking is that excessive latent thought might start to introduce redundant or just less useful noisy information into the shared memory. The alignment operator has to work harder, and you get diminishing returns. It means you can't just let it think forever. You have to be strategic.
Okay, that makes sense. What about the other big one, heterogeneity? Can a small, fast model collaborate with a huge, powerful one?
That's the second key limitation. As it stands now, the framework assumes the agents share the same basic architecture. The memory states, the KV caches, they all need to be structurally identical for that lossless transfer to work.
So you can't mix and match?
Not without extra work. To get, say, a 4 billion parameter model talking to a 14 billion parameter one, you'd need to add things like trainable adapters or some kind of complex layer mapping.
Which would break the whole training-free advantage.
Exactly. It's a solvable engineering problem for sure, but it's a constraint on this current implementation.
But even with those constraints, the fundamental shift here is it's enormous. We're talking about LLM agents no longer being forced to use slow, clunky human language.
They can share these dense, continuous internal thoughts. It's a level of collaboration we've really only theorized about until now.
The conclusion seems undeniable then. Latent collaboration improves reasoning and gives you these massive efficiency gains.
All without any additional training. It really changes the entire landscape for what's possible with agentic AI. You can build much more sophisticated systems for a fraction of the cost and time.
So what does this all mean? I mean, the development of LatentMAS is really moving AI communication beyond the limits of our language into something truly native to the machine. So if these agents can collaborate and reason perfectly in a hidden space, invisible to us at machine speed, what new kinds of complex problems become solvable when the AI conversation is no longer textual, but just pure thought transfer? That feels like the frontier we just breached.
Yeah.
AI, the first frontier.